Hi, I'm Sanjana Reddy, a machine learning engineer at Google's Advanced Solutions Lab. There's been a lot of excitement around generative AI and all the new advancements, including new Vertex AI features that are coming up, such as Gen AI Studio, Model Garden, Gen AI API. Our objective in this short session is to give you a solid footing on some of the underlying concepts that make all the Gen AI magic possible. Today, I'm going to talk about transformer models and the BERT model. Language modeling has evolved over the years. The recent breakthroughs in the past 10 years include the usage of neural networks to represent text, such as word-to-vec and n-grams in 2013. In 2014, the development of sequence-to-sequence models, such as RNNs and LSTMs, helped improve the performance of ML models on NLP tasks such as translation and text classification. In 2015, the excitement came with attention mechanisms, and the models built based on it, such as transformers and the BERT model. In this presentation, we'll focus on transformers. Transformers is based on a 2017 paper named Attention is All You Need. Although all the models before transformers were able to represent words as vectors, these vectors did not contain the context, and the usage of words changes based on the context. For example, bank in riverbank versus bank in bank robber might have the same vector representation before attention mechanisms came about. A transformer is an encoder-decoder model that uses the attention mechanism. It can take advantage of parallelization and also process a large amount of data at the same time because of its model architecture. Attention mechanism helps improve the performance of machine translation applications. Transformer models were built using attention mechanisms at the core. A transformer model consists of encoder and decoder. The encoder encodes the input sequence and passes it to the decoder, and the decoder decodes the representation for a relevant task. The encoding component is a stack of encoders of the same number. The research paper that introduced transformers stacks 6 encoders on top of each other. 6 is not a magical number, it's just a hyperparameter. The encoders are all identical in structure, but with different weights. Each encoder can be broken down into 2 sublayers. The first layer is called the self-attention. The input of the encoder first flows through a self-attention layer, which helps the encoder look at relevant parts of the words as it encodes a center word in the input sentence. And the second layer is called a feed-forward layer. The output of the self-attention layer is fed to the feed-forward neural network. The exact same feed-forward neural network is independently applied to each position. The decoder has both the self-attention and the feed-forward layer, but between them is the encoder-decoder attention layer that helps the decoder focus on relevant parts of the input sentence. After embedding the words in the input sequence, each of the embedding vector flows through the 2 layers of the encoder. The word at each position passes through a self-attention process. Then it passes through a feed-forward neural network, the exact same network with each vector flowing through it separately. Dependencies exist between these paths in the self-attention layer. However, the feed-forward layer does not have these dependencies, and therefore various paths can be executed in parallel while they flow through the feed-forward layer. In the self-attention layer, the input embedding is broken up into query, key, and value vectors. These vectors are computed using weights that the transformer learns during the training process. All of these computations happen in parallel in the model in the form of matrix computations. Once we have the query, key, and value vectors, the next step is to multiply each value vector by the softmax score in preparation to sum them up. The intuition here is to keep intact the values of the words you want to focus on and leave out irrelevant words by multiplying them by tiny numbers like 0.001, for example. Next, we have to sum up the weighted value vectors, which produces the output of the self-attention layer at this position for the first word. You can send along the resulting vector to the feed-forward neural network. To sum up this process of getting the final embeddings, these are the steps that we take. We start with the natural language sentence, embed each word in the sentence. After that, we perform multi-headed attention, 8 times in this case, and multiply this embedded word with the respective weighted matrices. We then calculate the attention using the resulting QKV matrices. Finally, we concatenate the matrices to produce the output matrix, which is the same dimension as the final matrix that this layer initially got. There's multiple variations of transformers out there now. Some use both the encoder and the decoder component from the original architecture. Some use only the encoder, and some use only the decoder. A popular encoder-only architecture is BERT. BERT is one of the trained transformer models. BERT stands for Bidirectional Encoder Representations from Transformers and was developed by Google in 2018. Since then, multiple variations of BERT have been built. Today, BERT powers Google search. You can see how different the results provided by BERT are for the same search query before and after. BERT was trained in 2 variations. One model contains BERT base, which had 12 stack of transformers with approximately 110 million parameters, and the other, BERT large, with 24 layers of transformers with about 340 million parameters. The BERT model is powerful because it can handle long input context. It was trained on the entire Wikipedia corpus and books corpus. The BERT model was trained for 1 million steps. BERT is trained on different tasks, which means it has multitask objective. This makes BERT very powerful. Because of the kind of tasks it was trained on, it works at both a sentence level and at a token level. These are the 2 different versions of BERT that were originally released. One is BERT base, which had 12 layers, whereas BERT large had 24 layers, and compared to the original transformer, which had 6 layers. The way that BERT works is that it was trained on 2 different tasks. Task 1 is called a masked language model, where the sentences are masked and the model is trained to predict the masked words. If you were to train BERT from scratch, you would have to mask a certain percentage of the words in your corpus. The recommended percentage for masking is 15%. The masking percentage achieves a balance between too little and too much masking. Too little masking makes the training process extremely expensive, and too much masking removes the context that the model requires. The second task is to predict the next sentence. For example, the model is given 2 sets of sentences. BERT aims to learn the relationships between sentences and predict the next sentence given the first one. For example, sentence A could be, "A man went to the store," and sentence B is, "He bought a gallon of milk." BERT is responsible for classifying if sentence B is the next sentence after sentence A. This is a binary classification task. This helps BERT perform at a sentence level. In order to train BERT, you need to feed 3 different kinds of embeddings to the model. For the input sentence, you get 3 different embeddings: token, segment, and position embeddings. The token embeddings is a representation of each token as an embedding in the input sentence. The words are transformed into vector representations of certain dimensions. BERT can solve NLP tasks that involve text classification as well. An example is to classify whether two sentences say, "My dog is cute and he likes playing," are semantically similar. The pairs of input texts are simply concatenated and fed into the model. How does BERT distinguish the inputs in a given pair? The answer is to use segment embeddings. There is a special token, represented by SEP, that separates the two different splits of the sentence. Another problem is to learn the order of the words in the sentence. As you know, BERT consists of a stack of transformers. BERT is designed to process input sequences up to a length of 512. The order of the input sequence is incorporated into the position embeddings. This allows BERT to learn a vector representation for each position. BERT can be used for different downstream tasks. Although BERT was trained on masked language modeling and single sentence classification, it can be used for popular NLP tasks like single sentence classification, sentence pair classification, question answering, and single sentence tagging tasks. Thank you for listening.